Hello, my name is Dustin Keys, and I'm a graduate student at the Oregon State University Seafood Lab in Astoria, Oregon. Today I'm going to re-emphasize Clearwater recirculating aquaculture systems. We have already seen these in class, but hopefully I can add a little bit more information. Clearwater recirculating aquaculture systems are perhaps the most intensive systems, requiring many artificial inputs and managing outputs effectively. Since Clearwater systems allow the aquaculturist to control a wide variety of inputs, an array of species may be successfully grown. Here at the bottom you can see all the species that you can grow, although you can grow a whole lot more than that. And some of the better known ones may be shrimp, salmon, cod, sturgeon, trout, and all sorts of groundfish. So you'll notice that both freshwater and saltwater species can be grown using the system. The carrying capacity varies with the type of system used, but Clearwater recirculating aquaculture systems generally have the ability for the highest fish densities. Arctic char, for example, have been shown to successfully grow at densities greater than 100 kilograms per meter cubed, and tilapia may be grown at 60 to 70 kilograms per meter cubed if there is plenty of aeration and the water quality is carefully monitored. The density will depend on the species, but these generally higher stocking densities allow these systems to be economically viable because they're very expensive systems. Here you can see an example of some sea bream that are grown in Israel, and you can see how dense they are stocked in that tank. So we've seen this example before in class. This is the AKVA group example. But I'd like to include a link to their webpage so you can see their system for yourself, and it's quite intensive and, of course, quite expensive. Clearwater systems are perhaps the most challenging to discuss because there's no clear right answer because there's so many variables. Each system is slightly different from the others depending on the species that is cultured, the company preferences, design limitations, cost limitations. We already know that we need tanks to grow fish, but the water will need to recirculate at an appropriate rate. The water will need to be filtered. The water will have to have enough aeration, and that all needs to be carefully controlled or you're going to kill your fish. So I'm going to focus a little bit on the recirculation part in particular because that is a very important part, and that's where all the variables come into play. So the first thing I'm going to talk about with regard to the recirculation process is mechanical filtration. You generally filter the water through this example of a drum filter seen here, or you can just have a flat screen filter, but drum filters are more efficient than flat screen filters because they continually separate solids away from the water and you don't have the solids dissolving back into your water. So these types of filters will generally remove particles down to 50 microns. And the types of particles that are going to be removed are going to be ones that are able to be settled at the bottom of the tank if left in the tank, and they won't be generally suspended in the water. So to get the suspended particles that are less than 50 microns in diameter, we need a microfilter, and often a microfilter will be combined with pressure because the space in between the filtering material is so small that you need more pressure to push the water through and separate the water from the suspended microscopic particles. And as you can see here on the figure on the right, there's a little pressure gauge up there at the top. So microfiltration can be cartridges, bags, or very, very fine mesh screens. Although all of these types of microfilters are used depending on your system. You can also use what's known as a UV filter. You can see in this system here in the figure we have a couple microfilters there, and then off to the right it's this metal tube, and that is the UV system. And a UV filter may be used to control bacteria and smaller parasites. This filter in quotation marks, because it's not really filtering, it's basically just blasting the water with ultraviolet light. And bacterial and viral and small parasitic nucleic acids can't handle this intense radiation, because ultraviolet light is radiation. And so it's going to irreversibly cause DNA damage to occur. Another option for improving the quality of your water is ozonation, and you can use ozonation instead of a UV filter or with a UV filter, I suppose, although you're just going to be paying more money for both. But ozone can be used instead of a UV filter because you can get away with lower daily water exchange rates, and oxygen is produced as an end product. The half-life of dissolved ozone is only 0 to 15 seconds. Ozone is O3, and then it degrades into O2. But ozone is poisonous to fish, so your engineer needs to make sure that the ozonation tank isn't right before the water gets pumped back into the fish tank. You're going to need a couple minutes after ozonation of recirculating throughout the pipes or other filters before pumping the water back into the tank to allow that ozone to naturally degrade into oxygen. At the bottom here, I have included a link from a short course from the University of Arizona. If you want to learn more, there's going to be a couple more throughout this presentation. And it's a really good link. It's a really long presentation though, so it's really only if you're like super interested in ozonation. Of course, we've already seen plenty of information on biofilters. We've read biofilter publication, and a biofilter probably should be added because it's going to remove nitrogenous compounds like ammonia and nitrates, which of course will kill your fish. They can also be used to remove dissolved organic solids and even carbon dioxide, depending on the type of bacteria that the filter is harboring. And of course, there's different types of biofilters, but the basic premise is that you get something with a lot of surface area and push the water through it, and you grow bacteria on all the surface area. And the bacteria like Nitrosomonas and Nitrobacter will help move nitrogenous wastes and improve water quality. So the last thing I'm going to talk about with regard to the recirculation process is oxygen addition and carbon dioxide reduction. There are many ways to do both of these. For oxygen, you can just bubble it in during the recirculation process directly into the pipe to increase dissolved oxygen concentration, but this is kind of difficult to do because the dissolved oxygen concentration is actually dependent on the pressure, which will be dependent on your pump and how much head your pump is able to achieve, and the pipe length will also have an effect on your dissolved oxygen. So it is a little bit difficult to do, although the physical process of bubbling the oxygen in is not that expensive. For higher stocking densities, this may not be adequate enough to oxygenate your fish, your water, so your fish can have enough oxygen. So you can buy an oxygenator, and an oxygenator produces up to 90% pure oxygen. And this oxygenator is integrated directly into the recirculation system, and it produces the oxygen. But once again, you don't want to put the oxygenator right in front of your tank, or else you're going to have a lot of oxygen coming out at once right after it's being produced. So you will need a little bit of pipe length between the oxygenator and the water coming back into your tank. And you can actually buy what's called a liquid oxygen, and it's like pure liquid oxygen, and you can put that in there as well. And then for lower stocking densities, people will also do like what you do in ponds, where you have the aerators on top of the tanks, but you can't do this with the higher stocking densities. And here's a little example of an oxygen producing, mechanically producing oxygen. And you bubble the oxygen in the oxygen feed gas, and then it will go down into and flow through the pipes. And carbon dioxide may be removed by the bacteria in your biofilter, but at higher stocking densities, your fish are going to be respiring quite a bit, and you'll need probably a carbon dioxide stripper to remove carbon dioxide and sulfides. And a carbon dioxide stripper is just another piece of mechanical equipment in your already mechanically intense system. And I should mention that for these complex systems, you are going to have a lot of mechanical equipment, and it's going to be very complex, and an engineer will need to be consulted, if not hired outright, depending on how large the company is. Once again, there is a super good short course from the University of Arizona if you are particularly interested in oxygen and carbon dioxide. And they have a lot more information on what a carbon dioxide stripper, how it works, and what it does. So there's, of course, many other things that you have to control for. You do need to feed your fish multiple times a day in these systems because it is clear water. There's no food in the water. There's no algae, phytoplankton, diatoms, nothing. So you will need to carefully feed your fish and monitor their feeding habits. The temperature needs to be carefully controlled. You can grow a lot of different fish on these systems. Some fish will do better at 20 degrees Celsius, 15 degrees Celsius, 25 degrees Celsius. So you really need to know at what temperature your fish will grow the best and carefully monitor that temperature to reduce their stress, especially at higher stocking densities, because they will be more stressed out often at high stocking densities. Of course, you're going to need a pump because the water has to get through that giant recirculating process that you have with all the mechanical equipment. And you need to have a plan to handle all the waste that is generated, because especially if you have a very intense system and multiple tanks, you're going to be generating a lot of waste. Now to costs. There are many factors that go into cost: gear durability, maintenance of the system, and it really all depends on the type and quality of individual components that you buy. When you set up a recirculating aquaculture system, you really have to have a strong business plan from the outset before you even start buying equipment. Really, you need to know how much money you're working with, so you can budget for your equipment. Costs will also depend on the amount of capital you have at startup, because larger systems often have lower maintenance costs than smaller systems based on the cost per kilogram of product. And if you have a lot of startup capital, and we're talking millions of dollars for these systems, you can design a large facility that has a low cost per kilogram of product. And even if you and maybe like one other employee are going to run a small system, these systems are not cheap, and you're still looking at money in the hundreds of thousands of dollars range. And if you have a lower cost system up front, you're going to usually be buying cheaper equipment. That equipment will need more maintenance costs over the long term. And so for a smaller system, you may be economically dependent on your first few crops of fish right out of the gate. But if you have a lot of startup capital, you may not. I'm a bit money obsessed because I think that money is at the heart of everything. So I would like to direct you to this article down here at the bottom. For developing these courses, we had to include an article that we wanted you to look at, and I just included the short courses. You don't have to look at them, they're just for your own information. But I would like you to look at this article, and you may suffer reading through it, and I'm sorry, but really, money is the most important consideration of any business, and everything is going to cost money. All the equipment, complex system of pipes, tanks, personnel, especially depending on how large your system is, and then careful monitoring of your water quality, fish, feed. There's just so many costs. And this article kind of goes into the costs of recirculating aquaculture system. And that's the end of this presentation, and I would like to thank you for listening.